Good morning, everyone. We're very happy to have Jiafei here to present his excellent works. Jiafei is a PhD candidate in computer science and engineering at the University of Washington, advised by Professor Deirdre Fox and Ranjay Krishna. His research focuses on foundation models for robotics, with an emphasis on developing scalable data collection and generation methods, grounding vision language models in robotic reasoning, and advancing robust generalization in robot learning. His work has been featured in MIT Technology Review, ReQuire, VentureBeat, and Business Wire. Jiafei's research has been published in top AI and robotics venues, including iClear, ICML, RSS, Coral, ECCV, IJCAI, Column, and MLLP, and has earned awards such as Best Paper at Ubiquitous Robotics 2023 and a Spotlight at iClear 2024. He is a recipient of both the Astor National Science PhD Scholarship and the Astor Undergrad Scholarship. Now I will pass the ball to Jiafei.
Thank you. Thank you for the most detailed introduction I have gotten. Yeah, so hi everyone. As mentioned, I'm Jiafei. I'm a fourth and final year PhD. And today I'll be sharing some of the work that I've been working on for the past 3 years on my PhD, both mostly done in NVIDIA and also in the Allen Institute of AI. So I think like we're all roboticists here. So I guess like we all have a vision for robotics, right? And that vision, maybe you guys might be slightly different from mine, but my vision is that one day we hope to have this kind of robots in our homes that's able to, fetch our groceries or bring me a bottle of wine or sort of like clean up the house and reset the house to its perfect state and just chill there for like, not doing anything. And until I give a next instruction, the robot try to do something. But the problem is that we don't see this in our homes. You might, if you have subscribed to Nail for like $499, you might get some random guy doing teleop remotely from a distance. And in fact, all of these videos that you see here are purely teleoperated by a human operator. So the question I have is, what do we actually need to achieve this North Star? I think I would like to propose that we need a robotics foundation model that's capable of understanding instructions and also acts purposefully in unstructured and open world environment. And what do I mean by acting purposefully? So you see from the first video, that's a humanoid doing actions. But if you look at how humans does actions, or in this case, a real butler, you realize that the way he acts is very different. He first tries to reason about where to actually place the knife, arranging it perfectly in a precise manner with millimeter precision. So what is required here? It requires him to be able to understand that the knife is to be placed at the furthest end from the other knife, and the ability to develop this kind of spatial reasoning and connecting that spatial reasoning and generating the necessary low-level action required to solve this task. Or even in a sense where you have a butler that brings, us a bottle of wine, the butler should be able to know where he actually previously stored this wine because it's pretty expensive, and ability to sort of recall his past actions and observations and sort of retrieve that information requires him to be able to do episodic reasoning in the actions that he picks. Or even in this example, when someone is carrying your luggage for you, the person must be able to detect when it's going to fail in terms of losing his grasp, and also to be able to quickly adapt, in a way that's meaningful to actually recover. And that requires him to be able to reason about failure. So I think, what do we really need to achieve this North Star? I think obviously on the surface in robotics, we need to have textual manipulation. We need to be able to have these policies generalized to different objects and environmental perturbations. You need to be really good at instruction following. It can be language or image code. But these are all surface observation. And I think if you dive a bit deeper, based on the example that I gave, we also require them to have spatial reasoning, the ability to localize free space, and the ability to sort of connect that spatial understanding into the actions. And for episodic reasoning, we need robots to be able to, remember its past actions and observation, retrieve that information, and act upon it. And for failure recovery, we definitely need our robots to be able to not only just detect failures when failures is occurring, but having the ability to sort of come out with strategies to recover. And that requires the system to be able to actually understand what kind of failure actually occurs. So in my research, obviously, we want to also focus on the surface observation, which needs to lead to the whole notion of actions in robotics. But below this whole surface observation, there's another world which is mainly sort of supported by reasoning. So it goes from spatial reasoning, episodic reasoning, and failure reasoning, and that will be the topic of today's talk that I'm going to share. And in my context, what I mean by reasoning, it means to leverage structured intermediate inference to uncover implicit knowledge that goes beyond generalizing on any kind of patterns. And that sort of aligns with my broader research goal, which is to build general purpose robotics intelligence that's able to reason before acting. And before we sort of get to that, we need to be able to know how can we develop such general manipulation capability. I think is to understand that we need to take a trip down memory lane. I think in traditional form of robot autonomy, people focus on building custom robots that's often caged, and then having human expert as the programmer to sort of pre-program these robots, and then using that to be able to do very specialized tasks and try to achieve close to 100% success rate. But in today's new form of robot autonomy, we need more general purpose robot that's able to be deployed without being caged. And these robots should be able to exhibit general purpose behavior in diverse objects, environments, and scenes. And that's usually driven by a generalist model. And one of the most common formula of building such generalist models are mainly powered by the success of LLMs, large language models, and vision language model. And in robotics, we have seen a trend of that, whereby people use a vision language encoder to encode the state information and observation together with the robot state, and then sort of train it with a backbone LLM or VLM, and then jointly decode the actions to predict the necessary action for the robot to take control, and training this all for vision language action alignment. And that gives success to many of these pretty great models, like Gemini Robotics, M1, Pi, and Momo that I'm going to talk a bit about later. But the problem is that are we actually there yet to do something like this? I think today's generalist robotics models are built on these LMs and VLMs, but are they actually capable of doing some of this reasoning that I just mentioned? So for spatial reasoning, for example, if you look at this very simple scene and you ask, any kind of frontier models out there like GPT-4o, place the green tin can in between the two plates. GPT-4o will generate some kind of localization in the form of bounding box coordinates. Gemini, maybe the recent one will be better, but also generate some kind of bounding box. Qwen does slightly more fine-grained bounding box detection. And then Pivot from Google DeepMind tries to predict a point or a region that it thinks matches the language description, but still fails in doing that. So imagine you train a foundation model, robotics foundation model, using an LM and VLM that's not even capable of detecting simple spatial relations. Do you think the policy will be actually able to succeed in this task? I think the answer is no. So this is Pi 0, trained on millions of episodes and even fine-tuned for this specific scenario, tries to put a green tin can in the exact location that the user describes. And you can see that it actually just drops at the plate. But it's pretty good at dropping at the plate. Yeah. And beyond that, for episodic reasoning. So today's generalist models, actually, I will say that they actually struggles with this idea of episodic reasoning, because a very simple task in simulation that looks like this, which is to reopen the previous drawer. So there's only 3 steps in this task. You close the drawer that's open, you press a button just to simulate that you're doing some arbitrary task, and then you try to reopen the drawer. You realize that the robot fails in doing that. And this is one of the state-of-the-art 3D-based behavior cloning model for NVIDIA called RBT2, and it struggles to do that. And you can see you press the button, and when it goes for the drawer again, it goes for the top one. So it actually succeeded at doing the task, but it's wrong. And this is not surprising, because modern approach leverage behavior cloning, which is Markovian in nature. As a result, many of our end-to-end policies are actually memoryless. So it's not going to be able to solve tasks like this. And lastly, for failure reasoning, for us humans, when we look at a video as simple as this, a robot doing tasks, which happens pretty common in the real world, the robot drops the apple and still try to continue doing that task. And if you ask any of these frontier models out there right now, what actually went wrong? The robot even succeeded at doing the task. If not, tell me why it actually failed. I realize that.
You might share the screen.
Oh wait, I'm not sharing my screen. Okay, sorry. Great. Oh. Okay, am I sharing? Yeah. So if you ask models like GPT will give you an answer that seems legit, but it's not legit at all. You ask Gemini, Gemini will basically give you a binary yes or no guess thing. So you're not really sure that it's correct. You ask open source model, it's really bad, because you just hallucinate random stuff that makes no sense at all. So we are still far from human level capability of reasoning about failures in the context of robotics. And so coming to that, I think in my work today, I'll try to present 3 papers that focus on solving or tackling some of these by providing new context. So for spatial reasoning, I'll talk about this new paradigm of training robotics foundation model, which is called reasoning in space. And for memory-based, I'll talk about this work called SEMTOE, which focus on building memory-centric robotic transformer. And for last one, for failure reasoning, I'll focus on how can we generate failure data at scale and able to train some of these existing VLM models to be able to detect and resolve failures. So let's start with spatial reasoning with MoMoET. So I think we all agree here that spatial representation matters for building such robotics foundation model, but many of these models today are actually ungrounded in action. And as a result of this, there's a weak tie to this observation, and many of these models has poor generalization, often fall out of distribution from this training data. And also, like for example, like in this case, where physical intelligence will not be able to, Pi0 will not be able to actually find the location. It's not because it doesn't know where the location is, because the underlying VLM are not able to even localize where it means to be in between the two places. And the reason it's not able to do that is because existing VLMs like GPT are always trained on this kind of localization data set that's very object-centric. But in this case, to solve this task, you need to have some understanding of spatial relation. And in fact, I will go as far as saying that it has to be able to understand spatial free space affordance prediction. And the way we sort of propose to solve this is actually by looking at how can we teach a VLM to be able to focus on localizing some of this free space. And that's with the work called RoboPoint. So imagine given the same natural language instruction to RoboPoint, RoboPoint will be able to generate normalized 2D coordinates. And if you visualize them, it basically point to the exact region that you're referring to. And that will be the first step towards solving this task and bridging spatial reasoning with action prediction. And the way RoboPoint sort of work in solving this task is very simple. We generate this kind of spatial affordance data at scale to actually train a VLM, but to generate such data in real world is not practical because you need to create ground truth annotation. So the way we did it is that we do it all in simulation. So we use NVIDIA scene synthesizer, generate millions and millions of houses, kitchens with different layouts and different object configurations. And because it's in simulation, you know the exact spatial relations between every object. So you can define this kind of object reference. And then the next thing you do is you try to draw these points on those objects. And the clever trick comes in where now if you draw these points, all you need to do is just remove the points and re-render that scene. Then you get this kind of free space annotation. You can also even generate object reference annotations in the same context. And using these, we generate a lot of this kind of spatial affordance prediction data. And we do full fine-tuning on Lava 1.5. That was one of the more popular open source model back then. We fine-tune it to be able to now take in natural language instruction and try to output this kind of normalized 2D coordinates that tells you exactly where the object is, or even this kind of free space annotation. So what can you do with RoboPoint? So RoboPoint can point, obviously. So what you need to do is just give observation and natural language instruction. In this case, pick up place the orange onto the bottom step. I think traditionally in robotics, people can design heuristic methods or systems to sort of solve this kind of problem. But with RoboPoint, all it does is that it just generates these 2D coordinates. And then with a bit of help with the depth camera, you are able to get it into 3D. And then using motion primitive, you can move it to the exact location that RoboPoint refers to. And because it is a general purpose VLM, so you can prompt it like ChatGPT. So this is me driving down Bellevue, and then I ask RoboPoint, how do I get to a carpool lane in this image? So obviously, for those people who drive, in US, the carpool lane is always on the leftmost lane. So RoboPoint replies me to the left of the leftmost car, and then I further prompt RoboPoint to give me the coordinate location of that. And if it's a full video sequence, you can get this kind of view consistent localization from RoboPoint. It's purely conditional on language. And with the release of RoboPoint, I think one interesting thing that we found out is that this is another paper that I did that looks into this pointing capability, language guided pointing capability in frontier models. And something interesting that we found is that all the old model or all the old chat point in large like in Qwen, GPT, Gemini, they cannot point. But the moment when RoboPoint is released, all these models suddenly develop that capability of pointing. So it might be coincident or it might be not, but the idea here is that we sort of inspire this whole new way of looking at using pointing as a form of intermediate representation for not only localized space, but you can use this for web-based agents or any kind of agentic frameworks. And this is also integrated into the NVIDIA hardware. So if you use NVIDIA Jackson, this is one of the starting tutorial kit using RoboPoint. But the question that follow up this spatial reasoning is that can such spatial representation go beyond pick and place? I think the answer is no. If you ask RoboPoint to pour me a cup of tea and you give that to a robot, it'll give you 2 points. You can't do anything with these 2 points. So the intuition is that we need a plan to be able to steer low-level policy. And I also go a bit further and argue that we also need to have some sense of depth to reason over its action, because in a fully closed loop perception control loop, you need to be able to know how far away are you actually are when you're trying to pour this cup of tea. And if you try to do all this reasoning just on language with like GPT-5, you realize the plan that's generated is not executable because language is not grounded in this context. So the way we sort of solve this problem is through MomoApp. MomoApp is the first fully open action reasoning model from Allen Institute of AI. And the idea is very simple. Give the same natural language instruction and the observation that the robot sees. MomoApp will try to auto-regressively start by predicting this kind of perception token. And if you try to decode this perception token, you'll basically get a depth map of the scene. And you can visualize this really pretty point cloud. And then condition on that, you will generate this kind of visual reasoning trace tokens. And then you try to ground this visual reasoning trace token in 2D space. You basically get a trajectory line sketching the next intermediate steps that the robot should take. So that sort of represents some kind of implicit plans. And condition on that, we generate the necessary action required for the robot to actually solve the actual task, which is pour you a cup of tea. So because Momo is a large robotics foundation model, is trained on a huge amount of robot data. And one of the most common tests for pre-training evaluation in robotics these days is using simpler, which reflects the training distribution of open embodiment. And that's what we did. So we compared with all these frontier labs model, VLA models, visual language action models. And we found that we're able to actually get really high performance for both visual matching and variation aggregation, which is like our distribution. And that's really interesting to us because the fun fact is that we're only using 39 times less data than what Pi 0 is using, and we're using 26 times less data than what Group M 1.5 is using. And that sort of still giving us the edge of this superior performance. And the way or the secret behind it is actually lies a lot in the data. And I'd like to talk a bit about this because the way we sort of train this robotics foundation model is focusing on only using open source data, and that's aligning with the vision of AI tool. But the problem is for anyone who use OpenX embodiment data set, you realize that it's not that great. What do I mean by that? If you look at deeper into OpenX embodiment, you see data that looks like this, which I can't really tell what is that robot doing because the resolution is so bad that most of the visual encoder has higher resolution than that. Or you have like data set that looks like this, whereby the robot is doing random things with like I don't even know how to describe this. Or you have Google spending millions of dollars to collect human tele data, but there's almost 9 seconds of video that the robot did nothing. So that's no ops for over 200 frames if your control frequency is at 20 Hz. And this is Droid. So Droid likes to grasp thin air. So I don't know what it's trying to grasp, but basically grasp for thin air. So you don't want to use this to train this whole set of OpenX embodiment data to train any of your generalist policy. So the first thing we did is that we spent manual hours with humans to actually manually look through this data, and we curate it all the way down to 190,000 robot trajectory out of 1 million trajectory. So we filter it significantly down and focus only on 3 data sets. And surprisingly, OpenVLA trained on full data set is so underperformed as compared to just using a fraction of it. And beyond that, that's not enough. So we need more data, but we need high quality data. So one of the early efforts that we try to do at AI2 is to try to scale data collection. And it's much harder than it looks on the surface. So we are not able to collect a huge data set, but we're able to collect about 10,000 robot episodes. And this focus on high quality data from multiple camera views, well calibrated with absolutely no scenarios of no ops. And these are collected across different households doing basic manipulation tasks. And we also focus on some tabletop tasks, that goes beyond just pick and place. And this data set contains over 100 tasks, and every task has repeated demonstrations. So it's not super diverse to a point that you actually hurts your performance. So you can use this to train even like diffusion policy or I don't know, any of the DITs. And the interesting thing is that we are still far from what Pi 0 is trained on. We're only at 200K and Pi 0 is at 1.2 million. So how are we able to outperform them? So I would like to always use this illustration of David versus the Goliath. And the secret behind this is in reasoning. So we have seen in language models that when you utilize chain of thought to reason for doing mathematics, we see a huge performance boost even though they're trained on the same data. But the problem is that if you apply the same formulation into robotics, I don't think it will work because reasoning in language is ambiguous for motion in space. So we think that to actually do reasoning properly in robotics, we need to be able to reason in space. And the way we do it is also by focusing on curating the data. So the way we do it is that we take a regular robot trajectory or demonstration that's collected that was used in the pre-training, we first annotate where the creeper is using MOMO, and then you connect that, you get a trajectory, you get a sketch forward in time, telling what's the next action to take, and then you can iteratively generate many of these kind of visual reasoning trace tokens. But then even with visual reasoning trace token, we think it's not enough to have a better understanding of the scene that it's actually interacting with. But many of these data doesn't have like a relative, have metric depth. So we actually need to have some kind of implicit depth understanding. So we leverage on this paper called perception token, which shows that chain of thought reasoning can be strengthened when you're able to reason over depth. So we use a BQBAE to generate this kind of perception token, and then we use this perception token, which represents the relative depth of the scene. We use that to annotate all the RGB image in the data set. And by putting this together, now you're able to auto-regressively come up with this kind of QA pairs, whereby now the observation is the robot's next frame, the current frame, and then the answer will be auto-regressively teach the model to predict these depth tokens. And then condition on these depth tokens, the model tries to predict trajectory tokens, and condition on that, they try to predict the action tokens to solve the task. Of course, MOMO is also trained with like visual reasoning capability. So we do co-training with a large amount of multimodal data sets. And this is just a mixture of all the data set that was used in MOMO as pre-training. We also have auxiliary data that focus on learning different auxiliary loss functions. And then we have also another thing called trajectory condition data, which give MOMO the capability to steer, which I'll talk a bit later. And the way we sort of train and infer MOMO is that we focus on three-stage training. We start with MOMO because we have to use MOMO. Yeah, MOMO is the VLM model from AI2. We start with pre-training stage, and the idea of pre-training is to be able to learn this kind of world knowledge through this large amount of multimodal data together with this 190,000 robot data. And then focus on the mid-training, which is only on this high-quality data set. And this time we'll introduce multiple cameras, we'll introduce action chunking, and that helps the model to better learn this kind of specific setup. And the mid-training stage actually give a 5 to 7 performance boost for any downstream task that you try to find. And for the last stage is fine-tuning or post-training, we focus on dynamically learn to adapt to new tasks in different embodiments. And the way you can sort of prompt MOMO is that you can do it through this paradigm of reasoning in space, whereby I just mentioned, auto-regressively MOMO will try to predict all these different tokens, giving you the final action token, which you can decode it to get the action to drive a robot. But the problem is that, you are predicting so much reasoning token, the model is going to be slow. For context, perception token is over 100 tokens, and that's not too feasible. So we're also working on iterating new versions of this so they can speed up significantly. And secondly, we are also having this ability to allow MOMO to be able to steer. So think of it in this way, because we are able to predict this kind of visual reasoning trace token, you can actually visualize it during test time, and that gives you an interpretable plan of what the robot might do. So what happens is that if you give a very ambiguous natural language, for example, put a toy on the coaster, there's 3 coasters there. If you don't describe which coaster, the model will just infer its own intent. And in this case, it tries to go to arbitrary coaster. So right now, it wants to go to a top. As you can see, after it picks up, it might actually want to change its mind and then want to go for the one at the bottom. But this is where human come in. So all I need to do is go to my interface, sketch a line during test time, feed that line into the model, and then that will control the robot to steer towards any of the different objectives that you have. So this works really well, especially from those pre-training data set that you see from OpenX embodiment. Not so much for post-training because there's much lesser robot data. But of course, if you test this in simpler, you can actually you can get really interesting behavior trying to steer the pause. And with that, we also did post-training evaluations on all these real-world embodiments, on these real-world embodiments from humanoids to bimanual to mobile manipulator, and we get pretty decent performance, but it's just slow. Yeah. And for Libra, obviously, we only compare with auto-regressive models because inherently, when you're using action expert, you're converting it from discrete to continuous. You are actually having an advantage over all of these auto-regressive models that does reasoning. And we are still able to outperform most of these models. I think the most recent state of the art is things that from NVIDIA. And we also try to investigate further to see whether is MOMO actually doing this grounded reasoning or is grounded reasoning actually helping. So in some of our ablation, we found that if you iteratively remove all these reasoning tokens, you realize that the last stage, which is just basically end-to-end going from observation to action, MOMO actually drop quite a lot in performance. And one of the things that people don't really do is that they don't evaluate VLA for their reasoning capability. They only focus on evaluating the VLM that was trained. But if your VLA model cannot differentiate a cat and a dog, I don't think it's doing any form of reasoning. So that's something that we did. We actually put all these VLA models to the test. We have OpenVLA, Pi 0.5, and body chain of thought together with MoMoWare. And we realized that all these benchmarks that actually was previously trained on, some of them just have catastrophic forgetting and they don't remember anything. And then we also compare it with the base VLM. Obviously, the VLM does much better. MoMoWare is still able to retain that kind of general knowledge. So it understands what's a cat, what's a dog, and basic reasoning capability. And we also show that when you're able to steer this policy, if you're trying to steer with this kind of visual sketch, it actually has a better effect than comparing with using open language instructions to try to steer your policy during test time. And these are just some of the use case moments of push for this whole notion of think before you act kind of paradigm, and it has been used quite broadly. And hopefully with this first topic, I'm able to sort of convince you that by defining this kind of chain of thoughts for robotics through reasoning in space, we enable models like MoMoWare to be able to surpass other baselines with much significantly less data, and that sort of pushes forward more of these kind of reasoning models for robotics. And the next part I'll talk about is the second work, which focuses on solving episodic reasoning. And feel free to stop me if you have any questions. For episodic reasoning, I think the most important problem that we're trying to solve here is that imitation learning policies are memoryless, and they're always having this Markovian assumption that your current observation and state will help you to predict your next. But that's not true in the real world. So if you look at a policy like RBT2, which is one of the state-of-the-art 3D-based behavioral cloning policy, you realize that it can't do a simple task like this. Basically, you have two buttons, you have one cube, and all you ask RBT to do, and you train with demonstrations collected from both sides, you ask RBT to try to press the button twice, whichever button that has the cube in front. So your language doesn't give away the answer. And if you try to evaluate RBT2 in this scenario, you realize the RBT2 first go for the button. As it's about to press, I remove the cube. You press the button, it remembers where it is, goes back to its initial state, and try to press it again, it goes for the green button. So the interesting thing is here, because if you collect demonstration 50-50, the performance you're going to get is also 50-50. That's because it doesn't remember its action that it took previously before the cube was there. But with SEM2Ed is able to solve this task with almost 100% success rate. Because the task is so simple, it's just like 3 steps. Okay. Yeah, so the way SEM2Ed solve this task is very simple. So we first focus on training a really strong multitask behavior cloning policy, and then we try to figure out what's the right representation to store past actions and observation in a computationally trackable way. And the way we did it is through this 2-stage training. Hopefully, we have, at the end of the day, a memory-centric robotic policy, and that's also inspired many work that focus on VLA or memory that you can look into. So the first stage, we focus on training this generalist manipulation policy, multitask policy. And the way we did it was that we took RBT2's base architecture, we made some really critical changes to it. So the first one is instead of taking the multi-view, the RBT does by re-rendering and pass directly into the multi-view transformer and do a one-time convex subsample to get this kind of action heat map, concatenate the action heat map to get a 3D region, and then zooming in for like the fine predict the next best point in the point cloud for the robot to sort of move towards using motion primitive. We introduced the notion of using a SEM2 image encoder to actually extract better visual features from the rendered RGBD observation. And then the second novelty that we actually proposed actually makes a huge difference is that this idea of a multi-resolution convex subsample. So RBT does a one-time convex subsample going from the output from the multi-view transformer all the way to like this kind of single channel 2D patches, which represents the action heat map. We do it in an iterative step by breaking it down. In every step we try to concatenate with the multiple resolution that came out from SEM2's image encoder. And the intuition behind this is that if your model can perceive better, it should act better. And that's true because if you're able to have this kind of hyper resolution, now your model is able to actually solve tasks much better. So we evaluated that on RL Bench 18 tasks, and we are able to be the state-of-the-art performance previously at that point in time. And then beyond that, we actually have a huge performance boost on high precision manipulation tasks, in this case, which is to insert the pig or to sort the shape. So compared to the baseline, it actually doubled in performance. And this is one example of that task. So it tries to predict the subsequent keyframes in order for you to actually put this pig into the block, and you realize the RBT2 actually miss it by slightly. In the real world, we tried it on this task called turn on the lamp. As you can see, it just has a millimeter precision. If your robot missed by slightly, you are not going to be able to grasp onto the knot and turning. And beyond that, because we're using this kind of SAM tools, image encoder, obviously you try different image encoders, we realized that it gives the added generalization and robustness to SAM2M. And the way we test it is with this work called Colosseum, whereby the idea is to do out of distribution during test time or training on the same training distribution during training. So it actually systematically perturbates different environmental change from lighting, texture, object size, blah, blah, blah. And then you realize that all the base model, the moment you change all these different things during test time, performance start to drop significantly. While SAM2M is able to retain pretty similar performance. So that ensures that your policy that's trained will be really robust regardless of the lighting condition that you're testing. And this is just one example of our distribution case. So we introduce some distractors into the scene, and RVT2 just goes for the random distractor that looks red in color. And the next stage, once you have a very strong generalist manipulation policy, we focus on this idea of memory. And we don't want to lose this manipulation capability. So what we did was that in the same architecture, we freeze the SAM2 image encoder together with the multi-view transformer that's responsible for predicting the next best action, but only fine-tuning the part that's in the center. And the way we did it is that we incorporate this memory architecture that was inspired by SAM2, which focused on motion tracking. And the idea is pretty straightforward. So after what comes out from a multi-view transformer, we will actually do an attempt with the memory attention together with what is actually stored in your memory bank. So your memory bank is a product of the action heat map that's being encoded. Obviously, the action heat map is a product also of the cross attention between your observation and action. And all these are iteratively stored in the memory bank. And then that will be a attempt with the next action prediction from the multi-view transformer. And that sort of enhances the action that's predicted for this current scene based on what actually in the past actions that was being stored. So the only downside to this is that because we're training a multitask policy, we need to know the longest task sequence in your multitask policy because that will be the context window of your memory bank. And we're also working on better ways to have more flexible windows. And the way we test SAM2M plus the memory enhanced version is through these 3 simulation tasks. And the way we design these tasks is also very interesting because many tasks in robotics, when they talk about memory, they try to design tasks that super long horizon. But the problem about long horizon tasks is that it might not be because of memory, but because of compounding error that the policy fails. So the way we design is that we make the task so short that it's impossible to fail. And every task, all the policy can succeed, but they only fail at the last step. So I'm not going to talk about the first one, which I'll talk about the second task, which is to put the block back into the original position. So the initial scene looks like this. The block will be spawned on any of these 4 patches. The data that's generated will put the block into the center, press a button to break the Markovian assumption, and then the robot will try to put the block back into its original position. And obviously, nothing is revealing from the language instruction for the model to overfit to. And this is what it looks like when SAM2M versus RVT, which is that strong baseline previously. And you can see that both of them does the task really well. So there's no like compounding error in this case, and then RVT chose a different patch. So the data was generated with a distribution of 25% each, so RVT got a success rate of 25% in Harry. So with this episodic reasoning, we are sort of able to inspire generalist robotics model these days to focus on this idea of having some form of memory either through retrieval-based methods or focusing on this concept of like having an active memory bank. And hopefully with this one, I'm able to sort of convince you that when you incorporate a memory augmented architecture into your policy learning, it helps to induce this kind of implicit episodic reasoning capability and improve your action prediction. And for the last one I'll talk about is AHA. And I think this one is pretty interesting. So it's a very catchy name because Eureka is taken. I cannot use Eureka anymore. But anyway, if you look at modern robotic systems that uses LLMs and VLMs, there's a ton of them. Everyone is using LLM, VLM to do everything and anything. And these are just some examples of those work. But I'm not going to cover all of them, but I'm going to focus on one word specifically, which is Eureka. Yeah, so Eureka is a word from NVIDIA. It's very interesting work. So the idea of Eureka is basically having these different simulation scenes, and you have all this like privileged information about the simulation, and then you have a language model to generate dense reward function. And you just keep iteratively doing this by generating multiple dense reward functions, sampling the best reward functions, and then train your policy again until you can get the most optimum reward function. And it's a very clever idea from Jason. So I think The whole thing about this is, if you think about it, it's a search problem. You're basically proposing many iterative dense reward function, iteratively keep searching until you can find the best. But the problem of this search problem is that you're relying on closed source model that you have no access to why it's predicting certain things. And that will lead to you having a performance that looks like this. So this is one of the tasks in Eureka. And the best reward function after 5 iterations, 16 sample, the robot slightly pushes the door open. But now if we change the way we look at this problem, and if I'm human in the loop and I do Eureka, after LLM generates the first dense reward function, I will train a policy and then I'll roll out that policy and human sits there and watch that policy and give an explanation of why it thinks it went wrong. And using that explanation to iterate the next cycle, you're able to solve Eureka in one step and getting a much better behavior as compared to the best reward function from Eureka itself. And with this notion, what if you replace it with a VLM? I think in this case, just now we realized now this VLM is able to actually detect when the failure occurs, like more so can it give you an implicit reason why it fails. And it's not hard to understand why, because now this is actually trained with robot data of failures. And I'm not talking about just failure data, I'm talking about failure data that's actually annotated with ground truth label. And this is something very new to robotics because many times we have a lot of this real world failure, but no one will spend the time to go annotate this data until maybe Robot Arena when they have Michael to do that. But anyway, so in this paper, we realized that, okay, now if you have a task that looks like this, human has to manually annotate every single video, explaining why it fails, at which point it fails. That's a huge amount of work. So when we think about this, we look at how can we generate failure data at scale. So the way we did it is that we focus only on simulation because we believe that semantic reasoning can be transferred sim to real without any kind of gap. So the way we did it was that we actually systematically generate failure trajectory at scale in a programmatic way in simulation. So you give any kind of demonstration that's successful in simulation, if it's a single manipulator, there's always a few common modes of failure. And we systematically sweep through all these successful demonstrations and we alter those trajectories in a way that's meaningful. And then now you're able to actually create failure trajectories. And these trajectories will fail intentionally. And when your success condition is trying to detect, you always detect fail. And by doing this, we can programmatically generate a bunch of these QA pairs of failure trajectories and explanation to explain why the robot failed. And you know exactly at which time step it actually fails. And by doing so, we created AHA failure reasoning dataset on top of our bench 100 tasks. And this dataset is all trajectories that fail. So nothing will work in this dataset. And this is just the overall distribution. Obviously, we have a really fine-grained definition of failures for translation errors, rotation errors, going to like positive, negative sides. And we use the same kind of paradigm to train our VLM model to be able to actually reason about the failure similar to RoboPoint. And we also incorporated VQA datasets and localization datasets for co-training so that it can better generalize. And this is the model that we train. This is AHA 13 billion. If you give the same task without humans annotating it, and you ask AHA the same question, AHA will give you the answer, which is that no, the robot slips the milk as it's trying to pump. And by doing so, we want to evaluate its ability to solve reason over failures for AHA. So we are not only testing on the same domain, so we test on out of distribution tasks, that means tasks that was held out from training, but in the same simulator, we test on Suran's dataset, which is called robot fail. It's totally different embodiment, and these are real-world robot data that collected by Suran. And then many skill, we generate a different set of failure demonstrations for different tasks to mimic the distribution shift across domains. And when we evaluate, we realize that our model is able to outperform both open source and closed source models at that point in time. And we evaluate not just on binary success, but also we evaluate on the semantic meaning of all these language models, trying to explain why failure occurs. And we realize that, for example, robot fail, GPT-4o with in-context learning gets you binary success detection of 50%. That's random guess. And we are able to push the number higher with AHA's ability. And furthermore, we show that AHA is able to retain general world knowledge, and it actually works really well with scaling with more data. So that's one of the perks of trying to generate more simulation data, successful demonstration simulation, and perturbate that to create counterfactual data sets. So what can you do with a VLM that can detect and reason about failure? So obviously you can solve Eureka. And the way we solve Eureka now is that if Eureka generates a dense reward function in the first iteration, we use the raw that was generated, feed it into AHA. AHA gives you an explanation of why it fails. we use that to actually condition on the LLM's generation for the next iteration. And all it did was that it introduced a penalty along an axis, and then the policy is able to succeed in learning. And we also show that you can use AHA for replanning. So this is the work from Leslie's group that focused on using open world TEM systems. So you use LLM to generate a PDDL style plan. It runs in TEM, and then we use that to detect whether the trajectory fails, and we recorrect the PDDL plan using an LLM model. And you can also use AHA for like binary success detection in this kind of open vocabulary data generation pipelines. In this case, it's meant anything. And then we show that by having a really good LLM to do binary success detector, you're able to improve system success rate significantly for methods like this. And hopefully with that, I sort of convince you that direct sim to real transfer is feasible, at least in a semantic level. And this helps to actually improve some of this robotic system that heavily relies on LLMs and VLMs. And at the end of the day, with all this work, hopefully I try to convince a new idea, which is that instead of an action perception loop we still need, we maybe can have something called action reasoning loop, where the model is able to do reasoning and then condition on its reasoning to predict the necessary action, and refining on the action to improve on its reasoning capability through further exploration. And here are just my collaborators. And thank you. I'm also on the job.
Thank you.